paper where I am writing or about to write? I have not yet written.
Yes, sir.
Okay, fine. So let me look at the next, perhaps most important operation, that is, I think we have already covered in the last class, adder and subtractor, right? So a single digit adder subtractor, we fondly used to call it a calculator, adder subtractor. So we have done it for a single digit. I think some of you have even submitted that so-called challenge problem. And what comes just after addition and subtraction? What is the next most important stuff you think that I mean we should take up?
So multiplication, division.
Multiplication. Okay, so division, I think maybe in this lab we may not take up, but certainly multiplication will be the next one. Now, when you have used the adder or subtractor module, what is the actual arithmetic chip that you have used? Do you recall the number or
7483.
7483 you have used, which is basically a 4-bit adder? And probably you know what is the difference between a combinational circuit and the sequential circuit. In your theory class, I think it must have been discussed by now. So the 7483, what do you feel? Is it a combinational circuit inside or a sequential circuit? Anyone can unmute and say. 7483, this 4-bit adder, is it combinational or sequential? Do you know the difference, first of all?
Sequential.
What is the difference between combinational and sequential?
In combinatorial circuits, the output depends on the present value of the present state of inputs, and sequentially depends on the history of inputs as well. Like the sequence in which the inputs have been fed to the circuit.
So just review your answer, because you said it is sequential. So my question is actually only about the adder, just 4-bit adder chip that you have used. I'm not talking about the full circuit that you have made. So I'm simply talking about the chip that you have used as a 4-bit adder 7483, which you are having.
Combination.
Okay, so I'm having two different answers now. So maybe I think both of you may review your answer and come to a common conclusion. So Amritaksha.
Yeah, if you're only considering the adder part, then yeah, I think it's combinatorial.
It's combinatorial, right? But probably when you said sequential, you thought about the full adder subtractor circuit, right? I mean, if I call it a system at all, so most probably we're talking about that system where you have got two registers, that ASCII keyboard. So is your answer pertaining to that whole system, that when you said sequential?
Yeah, I thought you were talking about
But yeah, you are correct in that sense, that if I talk about the whole single digit adder subtractor system, I mean whatever we have designed, that is a sequential, because it requires that key pressing in a sequence. You need to capture that sequence, and depending on the sequence, final result will be dependent. So certainly the whole structure becomes sequential, but as such, if I take this 7483 in isolation, that will become a combinational, that is basically a combinational stuff. Now, anyway, today whatever you will be designing, that involves a multiplier, a 4-bit multiplication basically operation. So we will design a 4-bit multiplier, but as such there is no direct chip that we will get for that purpose. 4-bit binary multiplier. So multiplication can also be done in different ways. You may design something which is a combinatorial multiplier. So maybe I'm just showing you with this kind of symbol, that maybe there will be 4-bit input coming like this, 4-bit input coming like that. And how many bit of output you need, I'm showing it with a bus symbol maybe. So here if I am having 4-bit operand, 4-bit operand, after multiplication, how many bit result I can expect at most?
7.
If it is unsigned, think about the maximum value that it can have. 4-bit means it will be having a range of 0 to
So the maximum will be 225, I think. The maximum.
15 into 15, 225. So for expressing 225, how many bits do you need? 8. 7-bit won't suffice. 7-bit can represent up to how much? Unsigned case?
127.
127. So you require 8-bit. 4-bit into 4-bit requires 8-bit. So I can probably connect several 7483 in proper manner to get a combinational multiplier. But today's experiment is actually to design a sequential circuit, because though I think Amitaksh was correct that the last time whatever you have designed single digit adder subtractor considering the registers in place, it was also a sequential design, but that is not having much challenge in designing a sequential circuit, because generally there are other timing issues and all. So today we will try 4-bit multiplier, which is basically a sequential multiplier. So I am calling it 4-bit sequential multiplier. Now, if I say 4-bit sequential multiplier, maybe it will not be able to qualify the design completely. There might be several different options for sequential multiplication. So let us just have a very quick look. I think I may not take much time today, so that you may try to submit it by 5 o'clock, because you need to practice a little bit during exam. You need to certainly submit within time. So suppose I am having two 4-bit numbers. I am representing them by say A and B. So let us say A, I am representing 4 bits by A3, A2, A1, A0. Whereas each these AIs, these are nothing but a single bit. So A0 is the LSB, A3 is the MSB. I am assuming 4-bit unsigned number. Probably you know about signed number. And B3, B2, B1, B0, another 4-bit signed number B, which we want to multiply with A. So one will be called multiplicand, another will be the multiplier. Now, upon multiplication, as we do in case of a conventional arithmetic multiplication, that is the decimal multiplication, which we are very much familiar with. So what do? We take one digit at a time. In this case, it will be a bit at a time, and then multiply the whole of this multiplicand. So then what are the possibilities? If it is binary, it becomes really very simple, because B0 can have only 2 probable values, right? 0 and 1. So if it is 0, then everything will become 0 when I write down this partial product over here, which is nothing but B0 times this. Now when I say B0 times this, what is the logical operation I am actually referring to? B0 should be OR, ANDed, XOR.
And
It should be ANDed, because if B0 is 0, everything becomes 0. If B0 is 1, then I am supposed to write down the multiplicand itself, A3, A2, A1, A0, right? So it is having possibly 2 values, I mean 2 probable values, and it may come by bit ending of this with B0. If B0 is 0, A0, B0 yields 0, and so on. If B0 is 1, it will yield the same number. So in that way, next time I will pick up B1 and once again do the same thing. So again, there would be 2 possibilities. So I need to write that partial product after shifting by 1 position. So just a conventional one. Only thing is that here everything is in binary, and the probabilities are very less, unlike the decimal number system. So here I need to then add these partial products together. There are 4 in numbers right now, whatever I have drawn. So if I note them down, so then how, am I getting 8 bits? So let me just try to find out that, okay, how many bits it will be there. So here I will get 4 bits. 4 bits either could be all 0. I'm just putting a green dot. They are not zeros. So this green dot may assume a value of 0 or A3. Similarly, this may be 0 or A2, 0 or A1, 0 or A0, something like this. So similarly here also, if I draw this is just to show the positional information of this partial products. So every time I am having either all zeros or the multiplicand copied itself. So now if I note down, this will certainly be coming over here. Now I need to add these 2 things up. and there might be a carry. So finally I need to add it up over here, add it up here, add up here, add up here, add up here. But if I count, I find only 7. You said 8 bit, right? 1, 2, 3, 4, 5, 6, 7 bit I am getting.
So there could be one more carry, right?
There could be a carry, because here the carries, if you find out, they are accumulating so that it can actually come over there. So because of that carry, it can really become 8 bit. So you are very correct. Now, there are, as I have mentioned, there are different ways of doing this sequential multiplication. So what we will do today is to choose this multiplicand. This one I am calling multiplicand. A is multiplicand, B is multiplier. So I will choose the multiplicand as a whole and put it over there. If I find this bit is 0, sorry, this bit is 1. If this bit is 0, I will make everything 0. Similarly, I will follow for all other partial product, and at a time I will add only 2 partial product. For example, I will look into B0 first. So let me use a blank paper. Okay. So I will first compute up to this point. So I will keep that result with me. Then I will look at the next bit, B1, and then I will find out this partial product. I will adjust it in such a way so that in this case, assume that, okay, this is non-zero, this is also non-zero. Then what I am having here, I will be having A1 here, I will be having A0 here. So I'll adjust it in such a way so that when I add these two numbers, A1 is now being aligned with this LSB of A0 and so on, A2 above A1, A3 above A2 and so on. So basically it is shifted by 1 bit position. But now for this addition, how many 7483 do you think will be required? Will a single 7483 suffice, or do you require more than one 7483? Anyone can unmute and say whatever you are thinking.
So like 4, 7, 4, 8, 3.
No, my question is still up to this point only, that adding partial product related to B0 bit of the multiplier and B1 bit of the multiplier. After unveiling the other two, maybe your answer I may take, but right now think of this one.
So one will be enough.
The output will be 5 bits. So can you justify that a single 7483 can handle up to 4 bit? So how can I accommodate 5 bit over here?
You need to add the fifth bit.
Right, this bit is directly, I can take it to be A0 if this is, non-zero, otherwise it is anyway 0. So I need to really add 4 bits. So here this 4 bit of this partial product along with the 3 bit of the partial product with maybe a 0 padding over here. So basically it is not even a full 4 bit addition. In this MSB position there is 0. I need not really have to think about this one. So fine. Now the total output, that will be how many bits? That will be 5 bit, right? Though I have used a 4 bit adder, but finally taking into this LSB, it could be 5 bit. Now I look into B2, and depending on its value, whether it is 1 or 0, I will copy the multiplier itself or I will copy 0. So then it is here. So I have, I assume that already I have added these two and kept somewhere means certainly on a register. And then I am going to add this 4 bit. So now, once again, do you still think that a 4 bit adder, that is 7483, would be sufficient to handle this situation, where I have already kept the result of the addition of two previous partial products? Now I'm going to add with this. So once again, for your opinion.
Yes, sir.
No, what is required? I mean, just a single adder, or now I require more than one adder?
Single is sufficient, sir. We can take first two as separate.
Okay. So maybe in that case, the next one, okay, just let me stop at this point and ask your friends that whatever your friend is suggesting, that this point also, we feel that maybe a single 7483 would be sufficient. If you recall, 7483 can handle only 4 bit numbers, so 2 4 bit operands. But I was suspecting that because this has already grown to 5 bit, then I am adding another 4 bit number with the shift. So then maybe a 7483 might not be sufficient. But your friend is suggesting that no, it will be sufficient. He said that 2 bits will remain constant. So all of you do agree, or is there any confusion?
So can you explain this part again?
I have not really explained as such. I was just asking you some question, assuming that, okay, you could think about and answer. So first part, is it up to this point, is it okay that after having two partial products, for adding them up, a single 7483 would be sufficient? So let us come back to that point first. And if that is getting clarified, then probably we can proceed subsequently to the other partial products. So this 5.
Yes, so that is clear.
That is clear, because here LSB is fixed, right? LSB need not have to be added with anything else. I can directly take that one without sending it to the adder. Adder, I need to send only the first 3 bit of the partial product and all 4 bits of the second partial product. So a 4-bit adder would be sufficient. Now, after storing that, that will become 5-bit, or can it become 6-bit after generating a carry? Is it possible that after adding these two partial product, it will become 6-bit, or it will remain in 5-bit?
It can become 6 bits.
It can become 6-bit, right? Or 5-bit? Sure. I mean, my question is, after adding this first two partial product, which as such is a 4-bit number, but because of this shifting, it appears to be 5-bit number. If I assume that, okay, there is a 0 for the second partial product. So then I am adding basically a 4-bit number with a 5-bit number. Now my question is, after adding these two, whether the resultant will be restricted within 5-bit, or it can grow by means of a carry certainly to 6-bit.
The final value can be of 6-bit, but the addition which we do, that final output will only be 4-bit at max. It can go to 5-bit.
No, I didn't get your final answer. After adding these two, my question is whether it can go up to 6-bit. So your answer is yes, or is it a no?
Yes, sir.
Yes, sir.
Once again, I think the house is divided. So think about that one. But anyway, let me just proceed about the next one. So whatever you have suggested, 5-bit, 6-bit, whatever. Now I am having another 4-bit number which is shifted by 2-bit position. That means I may assume 2 zeros are there. So I need to add this 4-bit number, a shifted version of that really, with the previously accumulated partial products. I am calling these two I've added, so that that intermediate value I am calling it to be that intermediate partial product. So I will be adding this 4-bit shifted number, I mean shifted by 2-bit positions, with that accumulated partial product. So what will be the requirement in this case? 7483, can I manage with a single 7483, or now I require two 7483 because some of you are suggesting it has grown to 6-bit, the previous addition result. So now a 6-bit number. Yes.
So the last 2 bits will be same, right? The last 2 bits of
last
the
2 bits, whatever we have accumulated will remain same, because here we are having 2 zeros. I mean, this shifted version, if we assume it to be filled up with zeros on the right hand side, so then certainly these 2 bits which you have already computed will not change. So only calculation is required into the most significant 4 bits. So is that part clear to all of you? Because that's a key point in this design. And this one can
Can you repeat it, sir?
which portion you tell me?
The important point you're telling.
Huh? Yeah.
So you said this is the key point for this experiment.
Key point is that whether you can manage with a single 7483 or not. Whenever I am shifting a partial product and then trying to add that with the partial, I mean accumulated partial product. So whether I can manage with a single 7483 or I require multiple 7483. So your friend is suggesting that whatever I have already computed, these bits will not change further on adding this thing, because here there are already zeros. So if you can appreciate that point, then you know that, okay, I can manage this addition with a single 7483. Otherwise, you will be ending up with using two 7483 at least, and that might be a wastage. If it can be managed certainly with a single 7483. So that is what I am calling a key point, that after shifting this and adding for adding new partial product, I can manage with a 4-bit adder, though the original operands appear to be much longer. So think about the last partial product. After accumulating that, that can grow up to 7-bit possibly, or 6-bit.
7-bit.
So even if it is 7-bit, then it will come up to this point, right? It cannot go beyond this. So if it is here, then once again, can I manage with another 7483, because then I need to add only these 4 bits with this much only, because the other portion of this partial product, which is nothing but 3 zeros, will be added to that. So in that case, those 3 won't change, right? So here also probably I can manage with a single 7483. So now think of that problem yourself a little bit, maybe a minute you take, that whether I require a single 7483 or I require multiple 7483s to handle this kind of operation. I've already drawn there, I guess. So it can handle 2 4-bit number with a carry in and certainly with a carry out. So basically the result will be 5-bit. So that is what we are having in a 7483, the 4-bit adder, combinatorial adder IC that you have used. So there are 4-bit inputs. The arrows are not visible anywhere clearly, but anyway, they are arrows.
So just a clarification. For storing the final output, will you use a 7-bit register or 8-bit register?
You will be requiring an 8-bit register, certainly. Okay. So now I think why this problem requires a little bit of thinking compared to the last experiment that you have carried out. I mean, unless you consider that challenge part and all, that was just simply drawing wires in your simulator, nothing else. So this one is having a little, I mean, thought process involved, because if you think of this one, maybe some portion I can draw for yourself. So first of all, what are the things you may require? Let us look into this, that how I am forming the partial products. I require to end these bits, that is the multiplier bits, 4-bit multiplier. I think don't get confused with this multiplier and this multiplier. I'm using this one as the first operand of the multiplication process. This is called multiplier. Sorry, this is called multiplicand. This I'm using as multiplier. So the multiplicand, I'm just copying over here, looking into 1 bit at a time for the multiplier. So how can I implement that in hardware? Can you suggest some mechanism?
We will use 2 registers. One will be a CISO and the output of the 2.
One will be PISO. You know what is that PISO? I think all of you in your theory class it has been discussed, or from some other source you know about that one already.
So we don't know. Same theory, not much.
So I don't know, sir.
No, you know about shift register, right? What is the shift register?
No, sir. So theory, like right now, like
okay,
Boolean algebra, those things are going on, theory class.
There is some theory we haven't even started in
Theory, I think your voice is becoming feeble gradually. So can you just let me know, I mean, where the theory part is, because probably for deciding about the next
Boolean algebra.
No, Boolean algebra means it is certainly not A plus B or those, what do you call those, Boolean identities.
Shannon's expansion theorem was the last thing. Later,
Shannon's expression was the last thing that we did.
And the Karnoff map, etc., it must have already been covered, right? 4, 5
no,
variables.
sir.
No, sir. No, sir. No, sir.
So given a truth table, you will not be able to find out its logical expression, or all of you know about the Karnoff map yourself, may not be.
So we know Karnoff map because a bit was covered in Introduction to Electronics course, but
Okay. No, because the next experiment, it actually involves that finding out some. Then at the end of today's session, I think I will just explain what you need to do so that you can come prepared in the next class. So anyway, let me first complete about this one. So whatever we are saying. So finally, what is your conclusion? I mean, a single 7483 will be sufficient, or you require 2 7483s?
So we require multiple, I guess.
Why do you say that?
So because like the inputs vary, right? So like when we are the first 2 bits, right? So the output will be contained. We will take the first 4 bits, basically the C out, and then the first 3 bits of the output, and then we'll feed into the another 783 and we will continue. And the last bit will be stored in the 8-bit registers.
Okay, so I think there might be some confusion amongst some other students also. So if they come up and say, is there any confusion, then maybe I can take another 5 minutes time to explain. Is it clear to all others? I mean, other than Krishnan?
So like the confusion is like when we are adding like one partial thing is added, then how we are using the same register to add the next partial thing and next partial thing.
Okay.
That is confusing.
Okay. So just let me explain a little bit more. So
No, so in theory it is clear, sir. I'm
okay.
only getting confused with the simulation part.
Sure. So just let me tell you a little more about some ICs that is expected to be used in this. So let me first come to the implementation of the partial product, that how you can get the partial products, and then whatever I think your other confusions are. So let me just take them one by one. So suppose I am having that so-called multiplicand A, whatever I am calling. Suppose I call it A3, A2, A1, A0. And what could be a good source of generating this multiplicand or this operands in a simulator? You have already used the simulator. So if I ask you to generate some 4-bit number, so what you may use?
ASCII keyboard.
ASCII keyboard, or there is something called a hex keypad, because you may not require this what do you call that, strobe signal now. So you may use even a hex keypad. That will be easier perhaps, but anyway, ASCII would also be same. So anyway, so I am having these 4 bits coming from your hex keypad or ASCII keypad, whatever. So now, can I have this type of arrangement over here, that I am having some AND gate, 2-input AND gate, connected like this to each of these input pins. And probably you have guessed what I am going to draw. So let us try to guess it. Can you tell me what I am going to draw now?
Shift register.
No, I mean the other input to the AND gate.
B0.
B0.
B0 will go to
All.
Okay, so let me take a common line which is going to all the inputs to AND. So now probably when those who have already told that it will be B0, others may appreciate, I guess, that if B0 is 0, then the output of the AND gate will become 0. And if B0 is 1, then the output of AND gate will be the multiplicand itself, A3, A2, A1, A0, I will get over here. So that part I will use as my partial product, right? So if you just put it over here. So this partial product, it is nothing but whatever right now I will get over here. So do you agree up to this point? Then I will proceed. Or if there is any.
So I have one doubt, like, will it be like last time that we have to like input A, then cross, then B or something, or will we use 2 different? Like, will it be like continuously you can stream input and get the output? This is what you want, or
no, right now I'm not asking that, because you have already done that kind of experiment, that from the keypad how do you get 2 keys in a sequence. So that will unnecessarily become bulky in terms of that circuit, and since there are I think restriction of 40 components, then there might be problem. So right now what I for this particular experiment, what I am asking that, okay, you generate 2 different operands. Maybe finally you will get it from the same keypad as you have done earlier. But for this experiment, you can generate them from 2 different sources, and then you can show the multiplication result. That is acceptable. If you can integrate with a. Is that your question, or is the question different?
Yes, sir. Like if we use hex keypad or ASCII keypad, then the maximum input that we can give is like 8, right? 8 or 9. Like we cannot give double-digit inputs.
No, this is not double digit, a single digit. I said 4-bit sequential multiplier. So 4-bit, the maximum value can be f into f, that is 15 into 15. Okay. So it's restricted to 4-bit only. So that is what I am saying, that you may use hex keypad. So okay. So any other clarification required up to this point, or may I proceed? Okay. So now at this point, I would get this partial product if I put B0. Now for getting the next one, what I am supposed to do?
So similar fashion, B1.
I need to feed instead of B0, I now need to feed B1 in this place. And then for the subsequent partial products, I need to feed B2 and B3. So this multiplication operation, probably you have already noticed that I was using the word sequential multiplier. I've written above there, I think, that 4-bit sequential multiplier. So why we are calling it sequential? Because this will be done in sequence. In one step, we are just finding one partial product, and then in the next step, we are accumulating with the present partial product with whatever is already accumulated. So in the first step, after applying B0 over here, whatever partial product I am getting, if I think about the accumulation process, then with what should I add this? Because there is no other thing prior to that. So how can you think of an accumulation process?
So we should use registers like 3 or 4 registers so that the corresponding partial products are stored the outputs, and then you can take them out.
Okay, so maybe in the sideline I can draw an accumulator structure. So just in a rough schematic form I'm drawing. Just let me know that, okay, whatever I am drawing, whether that makes sense or not, you may comment on that. So this rectangle, I am considering it to be a register of whatever width. Now the output of the register, I am connecting with an adder. So this is the adder symbol. I think we generally we generally see on a textbook. So maybe 7483 or whatever. So I'm not right now mentioning anything about its width. It could be 5-bit, 6-bit, 8-bit, or whatever. So the register output is going to one of the input. The other input is coming from somewhere else, that is from some external source. Okay, and the output of the adder goes back to the register. What do you call this structure? If I
Feedback.
Yes.
Like is it this is a kind of feedback, right? The output is fed to the input.
Output is fed to the input. So think about suppose I give some value over here, because I have shown it as a bus. So that means maybe 4-bit, assume it to be 4-bit, that I can apply any value between say 0 and 15 over here. So suppose I put let me give some value X, then I put Y, then sequentially I put Z, and so on. So then what will be the final value in this register after those cycles? In one cycle, and sequentially I'm putting X followed by Y and Z. Then what will be the?
It will be the sum of all those.
Sum of all those, provided that the register is cleared initially. If it is not cleared, whatever is the initial value, that will also remain added with that. So I may assume that, okay, it is having a clear, so any register you have used that is having a clear signal, a clear or reset control. Do you remember? What is the register you have used in your last experiment?
74273.
74273. Okay, so 74273, that is having a provision of reset. It is basically 8-bit register. Otherwise, there is something called 173. I do not think we use that in the lab, but anyway, that 173 is a 4-bit register. And if I remember correctly, then most probably it is having a reset. Just let me check it once. 74173 4-bit D-type register. There are two, yeah, clear is there. But anyway, I think since you have already used 273, you may use 273. So now suppose I plan to use a 273. 273 is a 8-bit register with clear or master reset, whatever you say. So for 8-bit register, do you think I can use that one for storing the final result? Because if I require it for accumulation, then it has to, where is that? It has to hold the complete result, right? So the result is 8-bit as shown earlier, or you have suggested also. So the whole 8-bit, then I can use a single 74273 for holding it, right? You may interact, otherwise I feel that, okay, I'm just talking to an inanimated laptop or something. So can I use 74273 to hold? Yeah. So 74273 I may use for getting the final result. So what we plan, I mean, this structure is actually called, whatever I have drawn over here, is called an accumulator, because essentially it accumulates this one. So this type of accumulator structure I can use for this. Now, if I am having a complete 8-bit adder, probably you do not have any problem in designing it. 8-bit adder means I need to add 27483 in cascade, taking carry output to the carry input of the next one and so on. But as such, I think while you are suggesting a single 7483 will be sufficient, so we will come back to that point. But maybe the data steering would be a little bit challenging in this case, because certainly when I add only the first two partial product, it is very clear that I do not require more than 17483, because certainly this bit, it can be 0 or A0 whatever. So this bit I can just take down, then the next bit and so on. So here, first of all, I think because we have already drawn the structure, it might be apparent that how do you generate those partial products in place, then I will come to the accumulation process. So as I have already drawn that initially you may need to give B0, then B1, then B2, then B3. So what if I store it on a register, say a 4-bit register, I store this, and then the last bit means LSB, I connect to that common input of the all AND gates. So whether that will serve the purpose? Once again, I think whatever you feel, you can unmute and you say.
Yes, sir.
But that will be only if I connect it to just one bit. It will be just taking B0, but then in the subsequent cycle, I require to feed B1, B2, B3 also there. So how do I shift the connection? Do you feel that this connection should be shifted from LSB to the next bit, then next one and next one? And what you are suggesting?
You can use the shift register and use the clock signal.
Okay, so now I think you are saying something called a shift register, which I think maybe some of your friends said that they are not completely aware. So let me tell you about that. It's called a shift register, where you are having a provision of, as the name suggests, provision of shifting the bits from one side to the other. So essentially what is inside a register, suppose when we talk about 74273, we say it's an 8-bit register. What is inside that? Probably last time we have mentioned about that. Flip-flops. What kind of flip-flops in general?
Generally
D flip-flop, okay. So we are having 8 D flip-flops that can store the values here, 8-bit values on a 74273. But I think some of you, as you are using those words, if I write PIPO, those who know probably they can answer. What is the full form of that?
parallel in parallel.
Parallel in parallel out. That means we are having, let me draw it on a separate paper. We are having 8 flip-flops as such independent of one another in terms of their input and output. Maybe the common clear line or common clock lines, these are there. So there are 8 such flip-flops. So maybe the input is D. So input is coming from one side. Maybe from top I am showing. There are 8 inputs coming for 8-bit register. And the output Q is once again I am taking down as the output of that flip-flops. So if there are 8 flip-flops, there will be 8 such outputs. And there will be a common clock line, which I may show also. Let me show the common clock line. So this is the clock line. The common clock line goes to all of them. I hope you remember the notations. If I put a small triangle over there, what does it mean?
It's a positively triggered clock.
It is edge sensitive, and in the absence of any bubble, it is rising edge triggered. If there is a bubble, that means it's a falling edge triggered. And I'm not showing that clear connection. There is a master clear on that is active low. If you make it low, all the flip-flops will become reset to 0. So that is what I think we are having in a 7483. Okay. So sorry, not 74273. 74273. Since I'm talking about 273, maybe I can show the reset signal also. So this is master reset bar or something, which goes to once again all of them. So if that becomes low, am I correct? I mean, if it is low, then it will get reset, or is it the other way around?
If it is low.
Okay. So for normal operation, I think we are supposed to keep it high, but for initial resetting purpose, maybe initially we can make it low. Achha, for today's experiment, I think as I was showing about this accumulator where I have drawn accumulator, I said that, okay, this register you need to clear first. So if you use that master reset for clearing, now today you may use something like, you know about some switch, some logic switch available on your simulator. I mean, those who have browsed the different available devices, I do not know whether you have seen that. So anyone has seen anything called switch in that? Particularly if you have used that ASCII keypad, then probably on the same submenu, you will find three things. One is ASCII keypad, one is hex keypad, that is having only
there
four.
are similar switches.
There is something called a logic switch, which looks like this, basically just a three-terminal switch. Okay, one side is showing as 1, this side is showing as 0. But you need to connect only this common point. So wherever you connect, suppose you connect it to the master reset. Now on clicking the mouse, it will flip between 0 and 1. So on clicking, it will come to 0. It will indicate that reset. And then so after running the simulator, if you click out in here, then it will be master reset. Once again click, it will go back to high position. So it will become cleared and it will be ready for further operation. So right now, I think you can use such a manual resetting operation. Then I may ask you to automate that one also probably. So anyway, now coming back to that, whatever we have been discussing about 74273. So that is called parallel in, parallel out, because parallelly you can put 8-bit numbers and you can get parallel output of such things. So this is called parallel in, parallel out. So I think some of you were also uttering this word PISO. I heard that some of you said PISO or PISO, whatever. So what is that?
Parallel in serial out.
Parallel in, serial out. So in parallel in, serial out, what is happening? Suppose let me show you a generalized version first. That in a parallel in, serial out, whatever be the number of flip-flops, it may look something like this, that a D input here, you can serially input into this D. This Q, I'm just showing it through dotted line right now, as if there is a connection from this Q to D, then from this Q to the next D, Q output to the next D, and so on. So now can you tell me what will happen if there is a common clock to all of them, and just I am having a single input line and a single output line from these ends, whatever is shown. So then I am having a common clock going to all the flip-flops.
The contents will essentially ripple out one after another.
Right. So whatever I am feeding here right now, they will appear over here, but after several clock pulses, depending on what is the total number of flip-flops in the chain. So in this case, if whatever I have drawn 4, so after first clock edge, it will appear here. This D input will appear over here. This input will travel down here in the second clock edge. In the third clock edge, it will go here. In the fourth clock edge, it will come out. Now, by this time, what will happen? When this content is getting shifted over here because of this clock edge, so what will happen to this flip-flop? If I have changed the input by that time, so it will latch that input here. Now it will come back over here. So whatever I feed over here, they will, as I think you have rightly put it in words, that it will be rippling through the whole chain of flip-flops down to the final output. So this kind of arrangement we will call shift register, that it will be able to shift the content. Unlike a parallel in, parallel out register, this I may call a serial input, serial output, or SISO, because I'm serially providing the input. Just a single input I'm providing and a single output I'm getting serially. What will be the delay depends on the number of total flip-flops. So this point, is it clear? It is not PISO. So I have written here PISO. Whatever I have drawn is not PISO. It's called SISO or serial in, serial out. So is this part clear? Then I will go to the next one.
So could you please explain how it will exactly work?
Okay, so just maybe we can spend a little more. Where is the mouse? Okay, the other window, you can clearly see and hear my voice. Just anyone can unmute and say.
Yes, sir.
Okay, fine.
Yes, sir.
Okay, so I think your friend has asked me to explain this shift register mechanism. So suppose there is no need to have a clear as such, but if I assume that, okay, it is whether clear or it is there something coming on the chat? So just let me read the chat once. I think the same thing. So he's asking, please explain how it is shifting. Okay, so let us assume that initially I have switched it on. Whether it can be cleared or not, I think I assume that, okay, I do not know what will be the present state of all the flip-flops after switching it on. That can be some garbage. So right now, suppose I put some value of 1 over here. Okay, so I'm just writing 1 at this point. So you consider that this 1, when I'm writing, it actually represents this value. So because it is accessible to outside, suppose I have provided a 1, but these are all internal nodes and this is the output node. So I cannot drive this one to 0 or 1. Rather, I will look into this one, that whether it is 0 or 1. So right now I cannot understand that, okay, what could be inside. So I'm just writing star, that maybe I can refer them as garbage value. Whatever is the initial value, they can be 0 or 1, whatever. Now, you remember the functionality of a D flip-flop. Whenever there is a designated clock edge, in this case, it will be a rising edge. Whatever is available at the D input, it will store that inside and make it available at the Q output. So is that functionality of a D flip-flop clear, or is there any confusion? Because that is
clear.
Okay.
Yes,
Right. So then what will happen? Whenever a particular clock edge occurs, so clock basically is something like a squarish pulse. So on the first clock edge, after I put a 1 over here, so this clock edge is actually received by all. It is not that it will be received by only this flip-flop. So everyone will look at its own input, that what is there. This flip-flop will find that 1 is here. This flip-flop will look at that some garbage value is there. So all the stars need not be same. I just indicated that, okay, it's unknown or garbage. So what will happen to this flip-flop, for example? What will be its output after the passing of this clock edge? The second flip-flop. I will take the first flip-flop later on. Anyone?
Garbage.
Garbage means basically this one. Whatever is this garbage. So this one will come over here. And for this one, what will happen? Earlier, it was having this value. So this one will be stored by this. Similarly, this one is finding this value at its input. This one will be stored and will become available. Now for the first flip-flop, because I have sent, let us say 1, or you can take it 0 also, doesn't matter, but I'm showing it with 1. So now this 1, it will be latched in this clock edge. So the output will become 1. So after this clock edge, suppose because it is in my hand, how should I change it? So after applying the first clock edge, after the occurrence of the first clock edge, before the arrival of the second clock edge, suppose I make it 0. So then what happens? Probably you can follow now that why this 1 was appearing here, because the input was 1 at the arrival of this clock edge. Now I am talking about a second clock edge that once again will appear simultaneously for all the flip-flops. So everyone will look at its input and provide that one at its output. So second flip-flop, now it is having this one at its input. So after the arrival of this second clock edge, it will become 1. And this garbage will go to the next one, this one. So it is basically as if the data is flowing from one side to the other. So this 0 will now enter as the output of the first flip-flop. So is that clear, or is there any other confusion? Anyone can unmute, and particularly those who have asked the question, whether it is now clear. Okay.
So this will use for the B, right?
Yes, I'm coming to that. This we will use for B.
And
But-
is there any specific ICR we'll have to create on
Yes,
that?
yes, there are. So this is not PISO. So just to, so I have just cut it out so that there is no confusion. This is called CISO, serial in, serial out. There is no provision of parallel input. Parallel input is the earlier one, parallel input, parallel output. I can load all the bits concurrently, but here it is not. If I have to populate a 4-bit number, then I have to do it in 4 clock cycles, serially sending the value from here. So I will send the LSB first if this side is LSB, then the next bit MSB I will send last, which will be stored over here if I need to send it like that. So anyway, now what about that parallel in, serial out? Once again, if I take 4-bit number, suppose I want to load all the flip-flops in parallel, that is concurrently. So they are once again that D flip-flop, D and Q, D and Q. So what is the problem if I try to load the other structure in parallel? Suppose rather than connecting just a single line to this D flip-flop, I can connect, let me, because I'm drawing a second figure, let me just show it like this. What will be the problem if I connect another input line to this D flip-flop? Can I load this D flip-flop in parallel?
But that kind of collides with that the wire or the connector which is coming out of Q.
Right. So I do not know whether all of you have appreciated Amritaksha's answer.
Yes.
So the problem is that if from this side there is an output Q, it can either be 0 or 1. And if I connect another line to the same D input, and if they are not matching, suppose the output of this one is 0 while I am trying to make it 1, then there will be, I think what the term he has used is collision or something like this. So sometimes it is called a contention, logical contention. So one is trying to pull it down to low, in other driver is trying to pull it to high. So there will be huge short circuit current flowing, some of the device get damaged and so on. So that has to be avoided under any circumstance, that the outputs I cannot short unless, I think maybe in theory class it has been discussed that something called open collector or open drain output. Are you aware of that? Something called WAD or WAD and.
Yes.
So accepting those situations, I think we are not supposed to connect two outputs. So in general, just I'm saying without going into the discussion of that thing because it will be covered in the theory anyway. So as a general rule, we understand that outputs cannot be tied together. So I cannot tie the output of this one with another line which I'll be driving from some other source. So here, then what is the possibility of parallel input? But still, I said parallel input, serial output. So I require the provision of inputting in parallel, but I also require to get the serial output. That means shift mechanism should also be there, but I need to load that one also. But then there might be a confusion for the flip-flop also, because think about this flip-flop. So I'm just personifying this flip-flop. So this flip-flop, what it will do? Should it get the input from the from its neighbor as a shifting process, or should it load whatever I am supplying from outside? So it must be in a dilemma that what to do. Should I load it in parallel from the outside, I mean, whatever is available, or should I get this value to be shifted? So how do you solve that problem?
We use some combinatorial logic to selectively pass one of the inputs, either Q or the value which is being loaded.
Okay, you have said selectively pass. So who will select?
The user.
The user. Okay.
There's a control.
Right. So if user is having a control, user can tell these flip-flops that, okay, now I want to load some number in parallel. And then after that, maybe I want to shift them serially. I want to get the output serially. So user has to tell by means of a control signal what the user wants to do. So certainly, I think there is a choice, as we are saying, for each of these flip-flop, that either it takes the output from its neighbor, that is basically facilitating the shifting process, or it can have a parallel load. So maybe I can identify two distinct operations. One is parallel load operation, one is that shift or the serial output mechanism. So shift or load, there are two distinct operations. Maybe I can give user a single control line saying that if this is high, then do the load. If this is low, then do the shifting operation. And accordingly, as you have suggested, that use some sort of combinatorial logic which will steer the appropriate signal into the D input. So do you suggest some block which I think you are aware of, which can choose from multiple sources and then finally take that into a single source
Multiplexer to one
multiplexer. Okay, so we are having another new term, and I'm sure some of your friends will say it has not yet been discussed in the theory class. So is that so? Multiplexer, is it a new term to many of you, or you are aware of what is a multiplexer?
Part of it, sir.
Huh? Yeah.
That is part of it.
Okay. So once again, I think maybe we can spend a couple of minutes about that. So a multiplexer, I mean, as I think some of you are suggesting, a 2-to-1 multiplexer, or it can be 4-to-1, 8-to-1, something like that. So a 2-to-1 multiplexer, basically, they use the word multiplex as a verb. So it used to multiplex between two inputs. If I call that as input 1, maybe I can mark it as A and B. So right now, whatever A and B I'm using, just a single line, a Boolean variable, and don't get confused with that multiplier and multiplicand. There also I'm using the same notation. So here, just with respect to this 2-to-1 multiplexer, I am saying A and B, they are just a single bit line. So essentially denoting a single Boolean variable, either a 0 or a 1. I can choose either A or B to provide it at the output. Now, who will decide? There is a control line which I may call S or select. So if S is 0, then I may choose A. So I'm just, this is something like unconventional notation. I'm just putting a 0 and putting a 1 over here, indicating that if S is 0, I will choose this port. If S is 1, I will choose the other port. So basically it is something like this, that A and B, I am having two input sources. I am having a switch. I can choose either A or B and drive it to the output Y. And the S, that select line, will choose the position of the switch, whether it is connected to A or connected to B. So that is basically a multiplexing operation. In short, we used to write mux. So a 2-to-1 mux or a multiplexer can choose out of two sources just by a single select line. If select line is 0, so I can either put it like this, that if select line, which looks like a different form of truth table, if S is 0, the output is A. If S is 1, output is B. You can probably draw a 8-input truth table because there are 3 variables A, B, S, all are inputs, and accordingly you can decide what will be that. But what will be the logical expression for Y? If I try to write down the Boolean expression of Y, then how should I write it? That when S is 0, then it will be equal to A, and when S equal to 1, it will be equal to B. So can I write a logical expression involving A, B, and S?
S bar A plus
S bar A plus.
Okay, so you know already why I am spending time really. Okay, so anyway, it will be A S bar plus B S. So it indicates that if S is 0, then this term becomes true, so Y will become A. Otherwise, if S is high, it will be equal to B. So that is a 2-to-1 multiplexer, and in this case, you will where I am drawing. In this case, you will be having a multiplexer connected with each of these D flip-flops. So for each D flip-flop, there will be a multiplexer connected at the input. Is the drawing visible where I am drawing?
Yes, yes, sir.
Okay.
So this multiplexer is like internally within within the IC of
Within the IC. I have not yet mentioned about the name of the IC, so that is why I have not yet mentioned. But as such, I mean, the IC that you will be using, it is inside that. So it is something like this. Say, let me draw it. This becomes a little side. Okay. So either I can choose from the red line, which is coming from outside, or it is connected from the output of this flip-flop. So probably now it is apparent, right? So output, I am having all 4 outputs.
Sir, where is the select line of the multiplexer connected like?
Okay. So select line, I think whatever we have been discussing so far. So can you tell me where it should really be connected to?
to like a control input is essentially a control input.
That is essential your control input. So whatever we are mentioning, that I think maybe I can put a border over here. So these are the parallel input lines through which I can load the D flip-flop, provided that this multiplexer is choosing the red input. I am having in all the multiplexers two input, one I am marking with red, another is with green. So the select line, as you are asking, so select line will be having, select line will be, where should I draw the select line? Here, does it look good? A select line is going to all the multiplexers. That select line I may call load or shift. So maybe if I write down like this, load bar, sorry, load or shift bar. So then what does it indicate?
The inputs are connected to one of the multiplexer, and Q is connected to 0.
The input is connected to one of the multiplexer, and okay. So if I make it high, no, I was actually asking that this notation, that if there are two options, suppose here I have written load and shift and put bar over one of them. So in this,
one is active and other is active load.
So when it is high, at that time it will be loading, right?
Yes.
At the other time it will be shifting. So it should load from parallel from outside. Whatever red lines I am drawing, this will be the outside lines 4-bit. So maybe I think if I write 1 and 0, it will not be visible. But anyway, that is connected to port 1. That if select line is 1, it will select that. What about select line 0? If select line is 0, then it will choose the other one. For 3 flip-flops, I have drawn the source, that it is from the other neighboring flip-flop. This multiplexer, I have not shown the source. So where should this line be connected to? There is no flip-flop on this side.
So maybe you can close the loop, like connect the output. The last one.
That is actually called a rotation operation, not a shift. I think that is also possible. But as such, I think to qualify it as a shift, we understand that, okay, it will not rotate it back.
But anyway, we are using parallel loading, right?
We can use parallel loading, but suppose there might be some situation where you still want to use it as a CISO.
Yeah, then we can have this connected to the input.
Right. So then I am having an input, which we will call, I am writing in full, I am calling it serial in. Okay. Now it is called paralleling serial out. So where are the output, serial output, where from I should take?
Green lines.
This green line, this.
No, the last one.
Or this one or this one?
Last one. The last one.
Last one is where I am pointing it right now?
Yes.
Okay. So that will be my serial out. But if I need, actually I can use it as a parallel out also. So it is not parallel in serial out only. Because if these are accessible, I mean, it depends on the particular IC, whether it is accessible to external pins or not. But whatever IC we will be using, it is actually accessible. So if I take this pin over here, along with these 3, it will become a parallel out, right? So these 3, along with this one, you can use it for parallel out also. So you can use it for parallel in, parallel out register also, a 4-bit, or in between you can shift it after loading in parallel. So for example, in our case, what we are supposed to do to get the result more efficient. More efficiently means in short time. Should I load the input serially, or do you prefer to have it in parallel?
Parallel loading.
Parallel loading. So maybe I can have this shift register that okay. Now comes the number 7495 is basically a shift register with this type of capabilities. Okay, is it visible where I am writing? I think earlier I was probably writing outside that visible zone. So I would just request you to refrain yourself from a few minutes, not to go into the simulator and check about the IC. I think you will certainly do that in a few minutes time. But let me just complete that one, because there might be a little confusion about its various controls, etc. So as 7495, you will find that just by looking at that, can you tell me if I say that okay, it is a 4-bit shift register, so then what are the probable inputs, probable outputs? Can you suggest something? If I try to draw the IC, how many pins I will see other than the power supply pins? Maybe for your reference, I can.
Parallel serial out or
That is parallel in, serial out, as well as I think whatever just now I was showing, that it is having a provision of taking all the outputs in parallel, and also that serial input, whatever I have drawn, that is also there. But certainly there are a single line, which either you can take it as serial out, or you can put it as a part of the parallel output.
Right. Then I think output pins will be 4.
Output pins will be 4.
4 for parallel load. Okay, I think we can maybe do it 4 pins for input as well.
Yeah, 4 pin for no, but this serial in, typically the source can be different. Source may not be same as this one. Okay, so that is why
Then 5 inputs and 1 loading pin.
Right. So 4 for parallel input and 1 for serial input. That takes it to be 5. Parallel output and serial output, I think this line can double about that. So there will be 4 output lines only. Okay, so other than that, what are the additional lines? I mean, some power supply will be there, but I'm not talking about that. There will be a load shift control. So if this is high, it will load in parallel. If there is if it is 0, it will go for this shifting. Now, do you think any other line will be there?
You will have clear, you will have clock.
It doesn't have a clear anyway. 7495.
Okay, we will have a clock.
You will have.
So actually, it is becoming difficult for majority of us to follow, because for majority of us, like these things are completely new, so a lot of things are getting like all together. So it will be better if we can summarize or go a bit slower.
No, coming in, I mean, what you prefer?
Yes, sir.
Many things are a lot new.
Yes, sir.
Because every time you are saying that, okay, this has not been discussed in theory. So do you say that if I tell that, okay, learn about a PISO, that will be sufficient, or should I explain the components? I'm not actually getting your suggestion probably.
Sir, at least you can do one thing, sir, like before they start, before having the lab tell us like what all things we need to read or something, they will come prepared. Because 1 or 2 people, those who have done it into the class 2, know it. Rest of us is like that only.
Yeah, I actually tried your suggestion earlier also. Earlier means in last year or so. But finally it turns out to be, I mean, those who have already read, they are only answering, the other people are not really reading. So, but still, I will do that from the next experiment. Okay, so let me see that, okay, how people are reacting. So anyway, just...
Okay, I mean, it's fine.
Yeah.
In the class, that will be also.
But it takes actually your time. But anyway, you are not submitting by 5 o'clock also. So anyway, now whatever is your 7495, so is that part clear? I mean, whatever till now is being explained, it will be having 4 flip-flops. It is having provision of parallel loading. It is having provision of serial output. So what you need for your purpose today, that serially you can initially take B0 here. After one shifting, you will get B1 here. Then if B2 was stored here, in another shifting, B2 will be here in another shifting. So in 4 clock cycle, after parallel loading of the 4-bit number, you will get B0, B1, B2, B3 coming at the serial output 1 by 1. So you need not have to really shift the connection of the AND gate that I have drawn a few minutes back. So this shift register, if you connect to the serial output of 7495, that is this pin. So just in 4 clock cycle, it can shift out this number sequentially 1 by 1. So that is the basic point. Okay, so to cut it short, but there might be a little confusion about the clock signal. You will find that if you yes, any question?
So where should the stroke signal of the shift register be connected? Like that thing is not.
So yes, so that I am coming. So here 7495, the clock, you may find that there are basically 2 clocks. So there might be a confusion about that. So let me just look at that, how they have drawn in the manual. So please download the manual, okay? So I think they are in at least one manual, they are showing it like this multiplexer. They have opened it using AND and OR gate. So just like a combinational logic, but you can possibly identify that it's a multiplexer. So the clocks just one thing, let me check. I believe it is acting on rising clock edge, but still if the clock is rising, CP falling, shifting, no, it is, I think, acting on falling edge. Okay, so then I think I should put a bubble over here. So please check. I think that is an important point. So now there are two clocks. They are showing one clock for shifting purpose and another clock. They are probably calling it clock 1 and clock 2 or something. So clock 1 and clock 2. So one is for shifting, another is for loading. So what do you feel? I think how these two clock signal I can feed into a single clock signal.
Multiplexer?
Yes, once again, I think we will be having some sort of multiplexer. So I will be having a 2-to-1 multiplexer that will pick up between this. So maybe I am drawing a multiplexer whose output is going like this. So once again, I think who will select the multiplexer? Same load shift line, right? That is shifting whether to use it for the load mode or for the shift mode. So depending on that, it will either choose clock 1 or it will choose clock 2. Okay, but there is a small issue. I think maybe in simulator you may not face that, but still let me apprise you of that problem. That if it is acting on falling edge, okay. So you might be having two different clock sources, if at all. I think in your design, you may not have two different clock sources. But if you are having two different clock sources and you just change the external control. So external control, you can change at any time, right? We used to call it an asynchronous input because it doesn't look about the clock age or whatever. So irrespective of the clock age or whatever, you can change certainly that load or shift line. But there is a actually actual requirement that when you are shifting that, what will happen if the clocks are not really synchronized? Why I am telling you that if you are shifting, say, from clock 1 and clock 2, and suppose one of the clock is like this, so it is high, and suppose the other clock is low at that time. Okay, suppose they are from two different clock sources. So a falling edge is occurring here and a falling edge is actually occurring here. So when you are, is it visible what I'm drawing?
Yes.
So when you shift it, let us say from clock 1 to clock 2 or clock 2 to clock 1, what could have happened? Suppose here I am shifting from clock 2 to clock 1. So look at this output, which is actually being given to the clock. So suppose I shift it in between when it is low, and consider the other situation also. I shift it when it is high. So could you guess what might be the problem? Because we know the flip-flops, they will actually act when it gets a falling edge. So what are the two probable sources of the falling edge? One is the falling edge of clock 1, one is the falling edge of clock 2. So can there be any other situation where it will get a falling edge other than this time instant when there is a falling edge either at clock 1 or either at clock 2? Could you force?
Yeah, during switching.
During switching, can you elaborate that? Okay, how it can happen?
After the falling edge of the first one, when the input is low, clock input is low, if we switch at that instant, then it suddenly goes to high, right?
Okay, so that may you are very correct. So if I yes,
So like, is it fine? Can you like tell what are like why are we having two clock signals? Like, can you just
because
explain this slowly again?
right. So because there are two modes, one is called the parallel load mode. I'm just writing load. Another mode is shift. Okay, so both are synchronous. That means the flip-flops need a clock signal, a clock edge rather, a falling clock edge to latch whatever is available at its D input. Now, because of the multiplexing arrangement, there are two probable sources. One is the external source, which we are calling it load, parallel load, or the serial in, or the and for the other flip-flops, it is the output of the neighboring flip-flop for the shift mechanism. But basically, there are two modes, load and shift. So, up to this point, it is clear, I guess. Load and shift, there are two operations.
Yes, sir.
Okay. Now, how do I choose them? Because of the multiplexing arrangement, I am having two sources. So we are having a control line that goes to the select line of the multiplexer. Just now we are talking about a multiplexer that based on the select line, it can choose either one of that. So it will choose either the load mode or the shift mode, right? So it is about the source. Now, when I choose load and shift, this particular chip is also having a provision to have two different clock sources. One I may use for loading, another clock I may use for shifting. I need not have to use the same clock for both the operations, because in some applications they might be coming from different other subsystem, okay, which might not run on the same clock. Loading might be done from somebody means some other hardware digital structure that might be running in one clock, and shifting, that is typically the serial in, etc., might be running by some other digital block. So they have kept a provision that we can have two different clock sources, that when load will occur, that will be irrespective of the shift clock, and when shift will occur, that will be irrespective of the load clock. I can control two clocks independently, the timings independently. So that is why, to give a little more flexibility, rather than having a single clock line, in that particular IC 7495, they have provided two clock sources. One, I need to give the clock, or I need to give it proper timing for shifting or loading operation. Other, I have to give it for shifting operation. So that is the point actually. So is it clear, or do I require further clarification?
Yes, it's clear.
Okay, but now what I am saying, think about this one. Suppose this clock 1 and clock 2, and forget about these waveforms. They might look a little clumsy or a little involved. Suppose right now, both are, because they are not in the same phase. So one of the clock is right now high, so there is no edge occurring. Another clock is low. Okay, so let us say CK1 is high and CK1 and CK2. So this is suppose high and this is suppose low. So maybe somewhere here, if you consider CK1 is high, CK2 is low. Now, as such, this is a steady state. CK1 is remaining high and this is remaining low. At some later point, I think it will once again become low. Now, suppose I suddenly shift that load shift control such that from clock 1, I suddenly choose clock 2. So what will happen to the output of the multiplexer? In this region, when clock 1 remains high, there is no edge, and when clock 2 remains low, there is no edge. At that time, suddenly, I shift this load shift control in such a way that the multiplexer changes its input selection of clock from clock 1 to clock 2. So could you tell me what will be happening at the output?
So the flip-flop will face a falling edge.
I could not make out. I think two of you are probably simultaneously saying. So Krishnan, can you come again and say?
So the multiple, so it will think that as if there is a falling edge there.
Because here originally it was high. Now as soon as I choose clock 2, it will become low. So when I shift just that load or shift signal from clock 1 to clock 2, because one was steady high, another is steady low, it will certainly generate a falling edge. So do you appreciate that problem? Because there is no falling edge either in clock 1 or in clock 2. just because of the changing of the load shift control at the inappropriate moment, that has given rise to some spurious clock edge. So is that problem clear? I think over this one. I may not have to overburden you at this moment, but still, because there is a provision, I'm telling you, it might happen in the lab when you are using 7495. But here, what we can do, we may tie them together to avoid any such confusion, because it's a small system. We use a single clock. We will not use double clock. But still, I believe that, okay, as a cautionary statement, I should have mentioned that there could be a spurious edge. So the rule is in general that whenever you are changing, the two clocks should be high. Both the clocks should be at the high level, so that there is no chance of generating any falling edge, because falling edge requires at least one of them should become low. Otherwise, it may not happen if both are high. So, but in this case, our 7493 will tie these two clock pins together. Once again, I think if you look into the simulator at 7495, you will find CK1, CK2, or maybe they are marking CP1, CP2. In some manual, it is called CK1, CK2. You may tie them together and use it as a single clock source. Okay, so you not have to think about two clock sources anyway. So right now, maybe the main thing that you have to think over is about the timing. So first thing what you need to do is to load the shift register, and you can give it from a fixed, say, hex keypad or whatever. So maybe from a hex keypad. So right now, to keep the matter simple, maybe I would ask you to use 2 hex keypad. But remember, in actual practice, maybe you will be having a single hex keypad, and by means of those registers that you have used earlier, you need to make it sequential. But as such, for today's experiment, to keep it simple, we assume that they are available in parallel, because already you know the technique, how to make them available in parallel, even if you are taking it from a single keypad. So we are relieving you from the burden of making that part. So you use 2 hex keypad. One is directly giving this to the AND gate input. The other hex keypad will be connected to the shift register. But then what will be the sequence in that case? You need to make that load shift control high initially. If this is the load line, you need to make it high. So manually, what you can do, once again, you can connect it to a logic switch. You can make it high. That will load this input over here. Simultaneously, you can also make the clear line of the 273 high, not high, I think it is active low to make it reset. So you know that in the first phase, before actually beginning the computation, this accumulator register is cleared, and this. Yes.
So, like, can you explain that part again? Like, I missed out that part, the load line of the shift register, that part. Can you say that again?
This shift register. So I'm saying that, okay, how do you start the operation? Because we need to give it proper sequencing. That what we are trying to do in sequence. So first of all, we need to load the 2 values properly. However, here it is a direct access. I think I'm just, once again, to keep it simple, I'm not telling you to load A into any register. Let it remain available all the time from the hex keypad. We know that, okay, how to make that available using 273 and all. So today, to make it simple, I'm saying that use just a simple hex keypad, where on your own switch wheel you can change the input for A. So just use a simple keypad, connect it to these inputs of AND gate, and you take another 7495, where you may. Rahul Ranjan, would you like to say something? Rahul Ranjan. Anyway, so your microphone is causing some noise. So if you want to say something, please say. Otherwise, you mute yourself. Okay. So maybe I can repeat, if because of noise you missed that. So from 1 hex keypad, you are directly giving over here. So it will remain all the time. You can change if you wish. The other hex keypad, that's the second hex keypad, you connect this to the parallel input of this shift register 7495. So to initiate the operation, certainly you need that so-called multiplier, this B3, B2, B1, B0 to be loaded over here from the hex keypad. So how do you load it? That will be done by applying a high load signal over here. So that I was telling, to give to a logic input switch. Just now I think I have drawn a logic input switch that it can flip between 0 and 1 on clicking the mouse. So connect this load line also to another such logic switch and click it so that it becomes 1. So that will ensure that it loads the value whatever is available on hex keypad at the next clock edge. But remember, it is not instantaneous. As soon as you make it 1, it will not load itself. It will wait for the falling clock edge. Till that time, it will not become available. So please remember that point. Whereas for the other keypad, since there is no sequential element, it will become immediately available over here. So in the first phase, or rather in the 0th phase, I may say, what two things you are doing? One is making this load high, also clearing this register 273 to 0 by setting master reset using another logic switch to 0. So till that point, is it clear? The initialization, this is 0 and this you are loading.
So we are switching on the load line by using a logic switch, right?
Using a logic switch, right. But remember, immediately making it 1 will not guarantee a load operation. That requires a clock edge to occur. So you require a clock edge. Where from you are generally deriving the clock edge in your other circuits where from you have got the clock?
Stroke signal.
So if you use a ASCII keypad, you can connect it there. Otherwise, you can use a pulsar circuit also over there. Okay. But if you feel you can use a strobe signal. I'm coming to the clocking a little later because clocking has something else to do also. So now can you tell me these 4 bits, where would you like to take? Because these are the partial products that we are using, that we are drawing. So certainly I think I need to come back to this point where we need to accumulate all the partial products. So now if you can tell me. Yes.
So like we need to store the subsequent partial products, right? So like we need more registers.
No, what do you mean by more registers?
Like sir, for storing the subsequent partial values of the partial products from the outputs of the AND gates.
So partial product, what could be the maximum size? That will be the size of the final result, right? The product. 8 bit.
Yes.
8 bit. So what I have drawn earlier, that is my suggestion. You can certainly do something else also that may work. So I was suggesting that if you put it in this form, maybe this is a very crude sketch, but probably give you enough hint about that. That if I put a register which is an 8-bit 74273, along with some sort of adder, it might be a little tricky. So if I connect it as one of the input to the adder, the other input is coming from maybe this partial product part where from we are generating those things, and then we are gradually accumulating that. So maybe initially after resetting it to 0, we first add this 4-bit. So initial value of register is 0, and now I am sending this partial product. Okay. So then what will happen?
Sir?
Yes.
Sir, like if we directly connect like the outputs of the AND gates to the adder, like the partial products have to be shifted, right, before adding. So how will that be like accomplished?
So think about that one, that whether I really need to connect all the 4 bits to the adder or something else, because the second operation, if I think about, first operation is trivial. Initially it is 0, adding with 0 is nothing. So if you think about just adding these 2 partial products, first 2, maybe I can cover this one. So I'm talking only about this portion. Okay. So then do you feel in my 7483, I should fit this bit?
No, so I think the first 3 bits of the first partial product and the last 3 bits of the second partial product should be added only, and the other 2 bits will be like constant.
Right. So that is the part I think where I said that you require to apply your thought process really. But here there is some hint. For example, when I have I have added this one with 0. So think about that one, because the next operation, as it is apparent that I do not need to put this one through the register, but still I cannot forget that bit as well, right? I need to remember that. So somehow I need to keep that in the register, but I do not need to pass it through the adder. So adder should get, you can just draw something which we usually call snapshot. That snapshot at this time instant when you are having the second partial product ready. So where do you get the second partial product? You will get the second partial product here when B1 is here. Okay, so just after 1 bit shifting, you will get the output here pertaining to the second partial product. Is that right?
Yes.
So when we are adding, where do we get the first partial product? Where is it stored?
A.
A means
Register.
a register. Okay, so inside the register, because the first operation, though it appears to be trivial, is what? I have cleared the register, then I have applied this 4 bit over here, and then it has added these 4 bits to 0, yielding a result of 4 bits. But now I need to add only 3 bits of result to this 4 bit.
Sir, I think I only need to take the output of the 3 bits of the register for adding. Like,
Think about, but you should not lose the 4th bit also. That will be significant for the final result. So there is a small trick. You need to think of this one. Hi, yes.
So, is there any such restriction that the order in which you have stored the bits in the B register, if register B, like can we feed the MSB first in the LSB at the end?
That you can do, but that is as such not necessary. But if you feel, you can certainly do that. But whatever gives you correct result, that is purely permissible. I think it is not that you have to. So probably you are suggesting that you should start from B3, right? B3, B2, B1, B0. Certainly you can do this.
You don't need to. In that case, we won't need to store that digit.
Think about that one, but still some shifting might be required.
Yeah, shifting will be required.
But just I'm asking. 74273, we have mentioned it to be a parallel in parallel out register. Can I make a shift register out of 74273? Is it possible?
Yeah, we just have to connect the outputs to the input, like external wiring.
Yeah, external wiring means whatever we are drawing in this serial input, serial output, that the Q output is to be connected to D. So if I just connect the output of one flip-flop, so it might be actually parallel in parallel out register, but I can connect this Q output to the input of D, this Q output to the input of D, this Q output to the input of D, and so on. So then it once again forms a chain. Okay, so that is another hint that 74273, if need be, I can use it as a shift in, serial out type of register, but certainly not parallel in serial out kind of thing, because I may not be able to use the parallel in portion, because in the absence of any additional multiplexer, I can guarantee that you may not be able to, you may not need to use a separate multiplexer. So 74273, maybe you can use it also as a shift register if you wish. And since there are 8 flip-flops, even you can choose 4 of them to configure it as a serial in, serial out. You need not have to use all 8-bit shift register. You can use it as a 4-bit shift register. Other 4-bit can still act as a parallel in, parallel out register. Okay, so think about that one. That is the actual hint. Once again, I'm repeating the statement. You can use the 7483 as a serial input, serial output register. However, you need not have to use all the 8 flip-flops in the chain. You can use partially. I mean, it might be 4-bit, it might be even 3-bit, 5-bit, whatever. So you can choose several number of flip-flops to connect them in a chain. Certainly, you cannot use for those portion a parallel input also. But the rest of the flip-flops, they can still work as PIPO, parallel in, parallel out. Okay. So if you remember this statement, basically there are 2 sentences I said. That some portion it can be converted into shift register, and you need not have to convert it the whole of it to a shift register. You can break it up into 4 or 3, 5 bits, whatever, and then use some portion as parallel in, parallel out, some portion as serial in, serial out. So probably that one will give you enough hint. Okay, so now
also, so how many 4-bit adders are we supposed to use?
Initially, if you are having any problem, you may use 2, but certainly I think the intended solution is using 1, because you have seen while analyzing that if steered properly, then it may not require a more than 1 748. So always the arithmetic requirement is for 4-bit added to another 4-bit number. Other bits remains constant. But how to handle those bits and keep them in the register, that you can think of. So maybe those bits which want to keep in a register, we can shift it because we do not want to load it. So anyway, I think I may not give more hint than that one. So finally, what I want is that, so let me repeat the procedure. We are clearing the register 74273, where we expect the final result to come up, the 8-bit result. So initially we are clearing, and then in the process of accumulation, the final result will come. And we are also doing in the same step, a shift register will be loaded parallelly with the so-called multiplicand.
Sir, your screen is freezing in between, like you can't follow what you are writing on it.
I do not know whether it is problem at my end or maybe the bandwidth problem at your end. Is it being experienced by others also, or?
No, sir. No, sir. It's fine.
Okay, but anyway, I think even if you are facing a problem, then I think maybe I can repeat. So wherever you feel that okay, you missed, please let me know. I will try to repeat that part. So phase 0. I mean, if I write it like this, phase 0. What is that? Load A. If I am loading here, so I am loading basically the other operand, that is B. I am calling it multiplier. I am loading here. So I'm just writing in short, load B in 7495. And also what we are doing in parallel, you are clearing the accumulator. If I call the accumulator register as R, where we will be storing the result, we are clearing that. So R is being fed with 0. So now how many clock cycle do you think it will take to get the final result? So in the final phase, you may put that number over here. After so many clock cycle, I will get the final result R, where I will get the R contains the product AB. So it is basically an 8-bit product. So how many clock cycles do you think in between I need for this accumulation? So one clock cycle I will certainly require for loading at this point. And this 74273, it's clear. I think you have used earlier. Is it asynchronous clear or is it synchronous clear?
Sir?
Yes.
Sir, like my screen was frozen like for the last 2 or 3 minutes. Now it is like, can you repeat what you said?
You are in which meet?
So the meet with less number of participants, like 14 participants, that meet.
Otherwise, you can just leave the meeting and join again.
Yes, sir. Now it is okay. Like earlier, for 2 to 3 minutes, it was frozen. Like, can you just repeat what you said in the last 2 minutes?
So, if you can tell me what is the last thing you remember you heard. Otherwise, the.
So, like the before, you didn't write. Use the green ink, like before the green ink.
Once again, actually, while writing with green, I was repeating the same thing. So you have not really missed. If you have heard about what I was saying when I have written in green.
No, sir. No, sir.
Okay,
that thing I missed.
Okay. Then let me repeat it. So I said that, okay, at the very beginning, I may call it phase 0 or initialization phase. I am doing two things together. One is I am clearing this register, and also I am making this shift register ready to load B in it. Because A will remain always available, but B I need to load explicitly into this shift register by making the load line high. So by using that logic switch, making it high, I am preparing this shift register to load B. Why I am using the word preparing? Because it will still not be loaded until the next falling clock edge occurs. So it will, if you count the number of edges, one edge will be required for loading of this one. At that time, you should keep it clear. Otherwise, it may get some garbage value. So then what will happen? In the next phase, you will get the output over here, because once it is loaded, B0 is available over here. So the first partial product will be available over here. So if you are feeding the first partial product to a 7483 properly, the other input is coming from the register which you have already cleared. So the output will be nothing but equal to the first partial product, which will be fed back over here and stored in that register in the next clock edge. So if I call that one as my phase 1 or the first clock edge for computation, So I would store the first partial product into the register. Now what will happen? Acha, by before the arrival of this clock edge, let me tell you what you need to do. You need to release this load line, otherwise shift operation will not happen. So once you have loaded this one in phase 0, you need to change it to the so-called shift mode by making it 0. You also need to release the release means if it is active low, you need to make it high, the reset, so that it can accumulate some value rather than keeping 0 within itself. So before the starting of phase 1, you should ensure that okay, you have released those load signal and the reset signal. Otherwise, it will take more clock cycles. Subsequently, you will find that it will be loading once again and resetting it. So this phase 1 basically begins once you remove those conditions of loading and resetting. Now in phase 1, what you are expecting at the reset, at that register are that it will, where I was writing.
First partial product.
It will be the first partial product. But there is once again a catch, because you are storing a 4-bit number into a 8-bit register, right? Where do you store? Do you store in the first 4-bit, that is in the LS side 4-bit, or in the MS side 4-bit? That you need to decide. Why I am saying this? Because in the next phase it will become apparent that when the second output will come, that is from this AND gate, whatever AND gate version of B1 will come, the LSB now is here, which need to be added with the next bit, not the LSB of the register. Okay, so you need to be a little bit tactical over here. I'm not telling right now how to solve it, because otherwise everything I'll be spelling out. So just think over this one. There might be multiple approach. There is not just a unique solution. There might be a multiple approach. But you just remember this thing. If you can design it properly, then you can manage with a single 74273 and single 77483. And certainly 17495 is also there along with AND gate. You remember by any chance AND gate number?
740 something.
Okay, you can always check it up. So that doesn't matter. Okay, so someone has written some message. No. Okay, so that is the only I should say a little bit of a twist is there. And actually you will find that the word whatever I am saying, you are having literally a twist. Okay, so probably after getting the solution, you can appreciate my sentence about that. So anyway, so then what will happen after another clock cycle? Then 3 things will be added in another clock cycle. All the 4 things will be added. But now you need to ensure that all the 8 bits are there in place in that register, so that you claim that okay, you are having you are having the result over here. So what I would suggest that before automating the structure, because if you count that the total number of clock cycle is 6, 5, 4 or whatever, then you can actually use a counter that counts the number of clock cycle and stops the whole process once the required number of clock cycles are there. Otherwise, I think there might be some garbage result stored, or you require some other mechanism to suppose you feed a 0 in the shift register so that it is not getting modified. So whatever way, I think you need to ensure that the register contains the final result, it is not getting altered. So my suggestion would be, for the control part, because you are not yet, I think, much familiar with how to design a control structure for a sequential design. Maybe you take several more theory classes to reach up to that point. So today, whatever I am saying, that all the controls might be manual. So starting from the initial loading of B and resetting the register R. Otherwise, I would have told you that, okay, you just start it and it will be automatically reset in the first cycle. It will be automatically loaded. Then it will automatically move to the shift control. So right now, I think maybe it will be slightly difficult for you to design. So I'm saying that manually you connect logic switch wherever you feel required. And then you, I think some of you are asking about the clock signal, right? You need clock. Where are the clocks required? One is in this shift register. 7495, you find it is active low or falling edge clock. What about 74273? It is acting on falling or rising edge. You have already used 273.
Rising edge.
It is on rising edge. Okay. So just think of that. Will there be any problem if you connect a common clock? Because in one case it will be happening in falling edge, it will be happening on rising edge. So if you feel, you can use one inverter after the clock, or you can use the pulsar. There are two outputs. One is Q and Q bar, I guess, or something. It says that complementary outputs are there. So you can use that if you want that both of them switches changes their content simultaneously. Or otherwise, if you feel that no, one can change at falling clock edge, one can change at rising clock edge, there is no issue, then you can still maintain that one also. So it is up to you. But right now, I will say that, okay, rather than using a pulse, if you use a pulsar, you have to use a very slow speed. So it is preferred that you use that manual clocking. So you know how to do a single step, right? So do not run it completely. In every step, you look into the register content, whether it is appropriate. Appropriate means you can actually find out what will be the partial product after adding 2 of them. What will be the partial product after adding 3 of them. After adding 4 of them, anyway, you will get the final result. So you need to check at each and every clock cycle that whether the register contains your expected value or not. Because otherwise, I think you may miss out that finally you will find result is not coming. Debugging will become difficult. So you follow single step, use a pulsar, or
So how do we do that? Like a single pulse?
In the simulator, you must have seen that how do you run the simulator? You remember that there is a man running. You click that icon.
Yeah.
So just beside that, there is another icon. There is a stair that a person is climbing a stair. Okay, so that is called step, basically. Stair means step. So that is just a single step. So if you just click it once, then it will advance by 1 step. Now there is another small issue. I think those who have already opened the simulator, you can check up. Then probably you are going to something called a digital option, where you are going for that simulation speed changing and all. From 30, you make it very slow, 1, 2, or whatever. So there on the top right corner, you find that something called unit. There are radio buttons called cycles and ticks, and ticks is originally chosen. Those who are in the simulator, you can also open and see.
Yeah.
Digital option on top right corner, it says units. So default is ticks. So cycles means if you put just click on that one step, single step, it will advance it by 1 clock cycle. So that is called cycle. Ticks actually, I think in my version, it takes 10 ticks to make a full cycle. Maybe I don't know. For Circuit Maker 2000 also, it might be same. So particularly to capture the spurious states, that if anything is happening between 2 clock edges, then you may need to step using that ticks, so that it is not advancing just by 1 full cycle at once. But otherwise, if you are running it for say 60 cycle, then you need to click 600 times if you use ticks. So choose it appropriately. Maybe you can set it to cycles first to see what is happening in every clock cycle. Otherwise, you need to click it 10 times. Yes.
So if we set it to cycles, then the simulation speed and all those things don't matter, right? Like if you're using that stepwise run thing.
Yes. So just try that one.
So could you please explain this part again, like where to go and
Which one? Let me know.
So just now you explained the stepwise simulation.
Stepwise simulation, I have not really explained the intermediate step. I left it for you to figure out. What I have mentioned is just the initialization phase, and I asked you to do it manually to load that one, to control that one. Even the clock, I am saying that use single step, so that is basically something like manual clocking. So initialization phase, I have said that load B into 7495 and reset that to 0. Rest, you may count how many clock cycles will be required to accumulate the full result in the register. And finally, after you put that number over here, I think it's not visible. I have kept a blank here. If you say it is phase 4, phase 5, phase 6, whatever, after that, I know that the register, the accumulator register here, it will contain the full result, that is the product of 8-bit. So you can try with some number like 7 into 5, but once again, I think since the result will be 8-bit, if you connect 2 7447 and 7 segment display, you may get the result which will not be in decimal, rather in hex format. So suppose you get, let us say something like this. Suppose you get a result which looks like this. So then how do you interpret it? I think by now you are experienced enough to interpret such results. Anyone can unmute and say?
210.
How much?
210.
No, that is in hex when you are connecting a 4-bit register, sorry, an 8-bit register into 2 7-segment displays. Here you remember this is nothing but a 273. Because here, right? So here you are using 4-bit of your results. I mean, I'm directly showing 4-bit. It will be through a 7447. So as if you are connecting that 74273 output to this. So then this 4-bit, whatever is value, it is saying C. C is how much?
10.
10, 1010. Okay. And 2 is how much? 0010.
32.
So in terms of hex code, if you think about, this is 2, this is C means 10. So in units place, it is 10. In the next place, which is having a weight of 16, it is 2. So 16 into 2 is 32 plus 10. That is 42. So under what circumstance will you expect this result? If you put the 6 in 1, 6 and 7. Okay. So check with all kind of possibilities. Say give odd, even, all kind of stuff. Because otherwise, if there is some problem, suppose you are not taking the last bit. So if you use always an even number, it might not become very apparent. So you use all possible combinations. 6 into 7, if you find okay, it is coming like 42. Try the other way around. You exchange the operands and see whether you are getting still the same result. Try with the maximum one, F and F. FF will be how much? 225. So you can convert that into hex once again and see whether you are getting the required result or not. Okay.
So,
Hi, yes.
so like, I mean, how are we supposed to check our result? Like for display, what should we be using?
Display, you are using 7447 and these 2 displays because you are finally checking 8-bit of result. So whatever is that 8-bit,
okay.
So you connect it, you are already having 7447 and 2 displays connected. So just connect that 7447 input to your 74273 output.
Sir?
That will also show you the partial results that you are storing in between. Hi, yes.
Sir, we can also connect like logic displays to the 8-bit output, right?
Whatever you feel for your debugging purpose. But it is, I mean, advisable that in intermediate step also you check that after resetting whether the content is shown to be 0. Because if there is a problem in the reset mechanism itself, or you may find sometimes that the shift register has not loaded the values at all because of absence of clock pulse or improper usage of load signal. So always check a probe, or you already know that there is another way in the simulator to check the status of a particular line. Are you using that one? That there is an icon with an inverter sign just after that man running, that is that run simulation. There are 3 keys, 3 buttons, out of which the middle one there is a inverter shown. Those who are having the simulator open, you can check.
Yes.
So you know about that one, that if you
it shows.
press that, right? So if you press that, it will show the status of a particular line. So if the line is green, what does it indicate?
Like 1, I think. The value is 1 for that line.
There are 3 possibilities: green, blue, and red. So one might be 0, one might be 1. What about the other one? That is a tri-state or floating or unknown. Okay, before the starting of the simulator, you may find that okay, it is remaining something like green or something. So you do not know what it is. So anyway, you can use all these debugging mechanisms, whatever you feel like. But certainly looking into the register content about the partial results, that will give you much clue. And also you can predict that what will be that partial result after adding, say, 2 shifted partial products. If there is any problem, you can immediately find them out rather than looking at the final result and wondering where the things have gone wrong. So to
So
reduce.
basically we use clock and then staircase will take like stepwise.
Yes. Stepwise means if you apply that step, I mean, if you click on that button and if you have chosen cycles as your unit, then one click advances it by one clock cycle. That means basically one edge has passed in between.
Okay, and one person, like Q will be fed to the shift register and Q bar will be fed to the equal.
Yes. Or if you are in doubt, you can always use an inverter also. Though inverter will be having some delay, but if you use cycle, I think that may not matter. So what personally I would suggest, because there are several things, as I think some of you have rightly pointed out, particularly theory has not progressed well. So how to reduce the total time, because if you consider the system to be a little bit complex, I may not even use the word fairly complex, it will be hardly having 3 ICs or 4 ICs as the functional ICs other than the display, etc. 7495, 74273, 7483 and that AND gate. So 4 ICs basically. So not a very complex system. But still, for example, 7495 may be a new IC for you. So rather than connecting it here and then wondering what goes wrong, you can just simulate that in isolation. That let me see that, okay, how this parallel load is coming, how this shift is working. So if you just spend additional 5 minutes of time, it will not be really wastage. You learn about that IC, about its functioning. If something, I mean, if there is any problem in your understanding, immediately you can find it out that, okay, this was, I was thinking wrong. Because after connecting and looking at the response of the whole system, the debugging becomes progressively difficult. So component wise, I think you can check whenever in doubt. Suppose 7483 you are already having experience, 74273 you are already having experience. There is nothing to really check about the AND gates. So only new thing is perhaps 7495. So I would request you to spend 5-10 minutes on 7495, its functionality. That is the only new IC. But then another, I once again should not use the word challenge, because you are taking up much more challenging job. But here, one thing which I have not really explained it and left it to you is that how do you really use a single 7483 in an environment where the words appear to be somewhat longer. But though we have actually analyzed and found out the actual arithmetic process requires no more than 4 bits of addition. So carry out will be coming out, and if I can capture that properly, then certainly this. So remember about carry in and carry out. So unless you connect them properly, the result will not be proper. So think about wherever the carry can be generated, how it can be put back to the register for its next usage. Okay, so that is the only tricky part. So just yes.
Since we are using X keypad, right? So there won't be any stroke signal.
There won't be any stroke signal. So you are right.
So you press like 7 into 8 or something, and then if you want to check for another input, so we have to stop the simulation and start it again and check it again.
Yeah, that you can do. Otherwise, you can once again go back to the same phase 0. So what is a phase 0? Using you can use a single switch or double switch, I mean 2 switches. But because one is active high, one is active low, otherwise you require an inverter if you use a single switch for initialization. So don't forget to flip this switch to load and this switch for reset. Reset means it will be low, it will be high for initialization. So without stopping the simulator also, you can load once again a new number if you have changed it in that keypad, because unless you load it, it will not be loaded, even if you load it, change the number. But here, certainly, if you change it in between, suppose only 2 partial products have been accumulated, and certainly you allow it to change, then the result will be some garbage. So certainly, I think as a user, you will not be probably doing that. So here, if you want to have a fresh calculation, then the best thing, either as we have suggested, you can stop the simulator, run it again, or you may load the number again after changing and reset this one. That will also do the same thing.
Sir?
Yes.
What do you mean run the simulation? Like, we are only using that stepwise run thing, right?
No, there is a reset. If you reset it, then it will go back to the initial state. So you'll forget whatever is the present state. There are 3 buttons, right? So beside that, there is that circular arrow kind of thing that will reset the simulator.
So one more doubt.
Yes.
For loading and resetting, how will we do that? Because I think we need to run for that. For the
Yes. So after running, you connect that load to high, reset to 0, then you apply a single step. If it is in cycle, then it will be loaded. But if it is in ticks,
Okay.
you require 10,
Oh, right,
10
right, I got
times.
it, I got it.
You require 10 times mouse clicking. So be a little careful.
Right, right.
So either use that checking by that color, that whether the value is really loaded into the shift register, or by putting a logic probe. I think checking by the color is easier. So why should we unnecessarily put another logic probe? So just check. If it is not loaded, then you may attribute it either to not changing it to that cycle instead of ticks, or there